Hello everyone. In this lecture we are going to start designing controllers using the Root-Locus approach. And as the natural first step, we will start with the proportional controllers. The proportional controllers are indeed one of the simplest kind of controllers that you can design, because they are only simply the gain that you need to determine what's the value. Here we have the design procedure for designing the proportional controller using the Root-Locus approach. The first step would be to sketch the Root-Locus for the given system. I guess it's kind of obvious that it should be the first step, as we are going to use the Root-Locus sketch of the system in order to design the controller. So first we draw the Root-Locus for the given system. Then we need to look at the requirements that we have for designing the controller. They will come in the form of transient requirements. The transient requirements are requirements that are dealing with the transient response of the system. And they will be typical in the form of overshoot, rise time, and settling time for a step response of the system. We need to translate these transient requirements into a feasible area of the Root-Locus in the S-plane. And we will assume that the T of S, the closed loop transfer function of the system, can be approximated as a second order system without zeros. Okay? So as the first, let's say, assumption, we will assume that the closed loop system of the transfer function of the closed loop system could be approximated as a second order system with no zeros. So we translate the transient requirements into some feasible areas of the Root-Locus. I will show you how to do it in the next slide indeed. We also need to translate the steady state requirements. The steady state requirements are typically in the form of steady state error for step, ramp, or parabola responses. And we need to translate these steady state requirements into conditions on the gain or KP. Over here, we will have some exact conditions. For example, we will end up, after translating the steady state requirement into condition of the gain KP, we may end up with the expression like KP should be bigger than or equal to 100. Yeah. It would depend on the kind of the steady state requirement. But once we translate them, we will end up with some condition on in terms of the value of the gain. The next step would be to find a gain KP such that we satisfy both transient and steady state requirements. We will see if it's possible or not. If it's possible, we will find the gain KP. If it's not possible, we will say that we need let's say a more sophisticated controller. Yeah, the proportional controller cannot let's say meet all the requirements. After finding out the value for KP, we need to have a look at the additional poles and or zeros of the system, because we have assumed that the whole system could be approximated as a second order system, but if there are additional poles or zeros, we need to consider them as well. We should plot the step response of the system with the design controller and verify if the transient requirements are actually met or not. If they are met, it means that our approximation was good. If not, we may need to, if they are not met, we need to modify KP further and try to meet all the requirements. And again, sometimes it's not possible to meet all the requirements using a proportional controller. In that case, we would say that we need a more sophisticated controller. For now, we will assume that KP is bigger than 0. In general, it could be any value, even negative values could be considered, but for the sake of simplicity, we will assume that KP is bigger than 0. Now let's have a look at how we can translate the transient requirements into regions in the S-plane. We can start by the overshoot. For the overshoot, usually the kind of requirement that we have is that MP should be smaller than MP bar. For example, we may receive the transient requirement in the form of MP smaller than 20% or MP smaller than 5%. Any value, yeah? It's just given in the form of a percentage overshoot that we need to be below that value, the step response of the system indeed. On the other hand, we know that MP and zeta are related to each other, and the relation is shown here. We know that zeta is equal to minus natural logarithm of MP over 100 over the denominator. We will find out the corresponding zeta and call it zeta bar to the value of MP bar. You can see that zeta bar is related to the value of MP bar. And I may remind you here that the graph that we had for MP and zeta was like this. So as one of them increases, the other one decreases, and vice versa. We also have another relation between zeta and theta. If you remember, let me maybe show it to you again. If we have the two poles here and there as a second order undamped system, we had this angle theta, and that theta is related to the value of zeta, with zeta equal to cosine of theta. So if you find some value for zeta bar, we will find some value for theta bar. Okay. So theta is the angle between the line connecting the pole to the origin. So this line with the positive imaginary part and the origin, so that's the line, and the negative real axis. So this negative real axis, this will give us the value of theta. Okay, so if we want to have MP smaller than MP bar, then we need to have the poles to be constrained in the white sector in the figure which is shown here. So the closed loop poles of the system should be located at this region. Or we can say that if we want to have MP smaller than MP bar, we need to have theta smaller than theta bar. And theta is here. This is in the theta bar. So if the theta for the system is smaller than that, then the closed poles of the system will remain within this area. So that's what we have for the overshoot. Then the next requirement is the rise time. For the rise time, we roughly approximated it as 1.8 over omega n. And usually the condition for the rise time is in this form. TR, the rise time should be smaller than TR bar. For example, TR should be smaller than 2 seconds. TR should be smaller than 1 second. Okay, the requirement is usually in this form for the rise time. On the other hand, we can find the omega n bar, which corresponds to the TR bar, as 1.8 over TR bar. And since we want to have TR is smaller than TR bar, this means that omega n should be bigger than omega n bar. And if you remember, omega n was indeed the distance of the complex pose from the origin. So this was omega n. If you want to have omega n bigger than omega n bar, then we need to draw a semicircle with the radius of omega n bar, and then the desired area for the pose will be outside this semicircle, because when the closed loop pose are located in this area, the omega n that we get for them will be bigger than omega n bar. So that's the desired, indeed, a region for having the closed loop pose of the system. The next one is regarding the settling time, the transient requirement that we have. For the settling time, we also have it in the form of settling. The desired settling time should be smaller than a given value. So TS 2% should be smaller than 3 seconds, for example, yeah. And we can have it for the 5% settling time as well. On the other hand, we know that the settling time is related with zeta omega n. 2% settling time is 4 over zeta omega n. And it's indeed the real part, yeah? Zeta omega n is the real part of the pose of the system. So if you want to have settling time is smaller than a given value, if TS 2% needs to be smaller than TS bar 2%, then we can say that zeta omega n should be bigger than zeta omega n bar. And zeta omega n bar is indeed equal to 4 times TS bar 2%. So we find out the corresponding value of TS bar, zeta omega n bar, which relates to the desired, let's say, settling time, and then we draw an area and say that the closed loop pose of the system should be located in this area in order to be able to satisfy the requirement on the settling time. So we had those 3 transient requirements separately. If we have more than one at the same time, more than one requirement at the same time, then we need to find out the intersection of the yellow areas, yellow highlighted areas that I just showed you. I may show it later in an example. The next kind of requirements that we have is called as the steady state requirement. It's usually regarding the steady state error for a given input like step or ramp. If you remember, the steady state error depends heavily on the type of the system. Whether system is type 0, 1, 2 or more, we can say that the steady state error to a specific input is either 0, it has some finite value, or it is infinity. When it is 0, the value of the proportional controller's gain will not have any effect, or when it is infinity. The gain of the proportional controller will have effect on the steady state error only when it has some finite value, and it would depend on the type of the system and the type of the input, whether it is step or ramp or parabola or any other input. Okay, so that's the main fact over here. So when the steady state error has a finite value, then we can say that the steady state error could get smaller if we increase the value of Kp, for example. So let's check it for this example. Gp of s is in the form of 1 over s plus 3. You should know that this is of type 0. There are no integrators, there are no poles at the origin. And if we use the proportional controller, L of S will be in the form of Kp over S plus 3. Now, if the requirement is that steady state error should be 0 for a step reference, if the requirement is this, then we can say that it is not possible to do it with a proportional controller. But if the requirement is that steady state error should be less than 10% of the reference step signal, then we can work on it. Yeah, we can say that steady state error is equal to 1 over 1 plus Kp over 3. So limit of L of S as S goes towards 0 is equal to Kp over 3, where Kp is the proportional gain. And then this should be smaller than 0.1, and out of that we can say that Kp should be bigger than 27. So this is the, in some terms, it's translation of steady state requirement. And then if we have steady state error being finite for a ramp or parabolic reference, again we can say that it is impossible to do it with a proportional gain, because the steady state error for those inputs is already infinity, and changing the value of the proportional gain will not have any effect. As another example, if we had Gp of S equal to 1 over S, and you know that this is a type 1 system, L of S in that case would be equal to Kp over S. In this case, if the requirement is that steady state error should be 0 for a step reference, then we can say that it is already satisfied and it doesn't depend on the value of Kp. Whether it's big or small, the steady state error is already equal to 0. But if the requirement is that steady state error should be smaller than 20 for a unit ramp reference, then we can work on it. For the unit ramp reference, we know that steady state error for a type 1 system is equal to 1 over Kv, indeed it is, where Kv is equal to limit of S L of S as S goes towards 0, and for our example it will be equal to 1 over Kp. So Kp here is the proportional gain, the gain of the proportional controller. If it needs to be smaller than 0.2, then Kp bigger than 5 will be the translation of the steady state requirement. If the requirement is that steady state error should be 0 for a ramp reference, then we can say that this is not possible with a proportional controller. And similarly, for a requirement like steady state error should be finite for a parabolic reference, again we see that it is not possible with this kind of controller for this kind of system. We can take analogous considerations for the rejection of the process disturbance, or D of T, as well, as we already have seen in the analysis of the closed loop systems. Something too important is that we will have the requirement in terms of the gain of the controller that should be bigger than some value, but you should always keep in mind that in some cases our system might become unstable if you increase the gain too much. Let me give you an example. If we have this example, as the first step we need to draw the Root-Locus. If you draw the Root-Locus, we will have something similar to this. Now, if the requirement for the transient response and the steady state error are such that we place the closed loop poles of the system over here, and then the requirement on the, let's say, steady state error gets tightened, meaning that we need to increase the gain even more in order to make the steady state error smaller. If we do that, the poles will move in this way. And if we do it too much, then the poles will end up in the right half plane and the system will become unstable. So that's something that you should keep in mind and you should avoid all the time. One of the main requirements that might not be even stated is that the closed loop system should be stable. So we shouldn't make the closed loop system unstable. Alright, so that's all for this video. In the next video, we will go through an example of designing a proportional controller for a DC motor, and over there we will see how to do it by referring to the material that we have learned in this lecture. Thank you for watching and see you in the next video.